NASA says there's no threat. The UN just made it an official target. Both statements are true. Both can't be right. And this isn't happening in some distant future or theoretical scenario. This is unfolding right now, in December 2025, with deadlines you can mark on your calendar and watch count down in real time. Let me lay out what we know with absolute certainty. On one side, NASA has maintained its official position that 3I Atlas is a natural comet from beyond our solar system. Interesting, yes. Unprecedented in some ways, absolutely. But a threat to Earth? No. They've been clear about this. No danger, no risk, nothing to worry about. It's a visitor from interstellar space doing what comets do. Move along, nothing to see here. On the other side, the United Nations activated its Planetary Defense Network in late November. The International Asteroid Warning Network, which coordinates hundreds of observatories across the globe, launched its 8th official exercise. But here's what makes this different from every single exercise that came before it. For the first time in IAWN's history, they chose an interstellar object as their target. They chose 3I Atlas. The same object NASA calls harmless is now the focus of a coordinated global monitoring campaign that runs until the 27th of January 2026. Stay with me for the next 15 minutes, because we're going to pull apart this contradiction piece by piece and examine what's actually happening versus what we're being told is happening. We're going to look at the timeline that doesn't add up, the scientific anomalies that can't be explained by calling this a normal comet, and the responses from scientists who are split right down the middle on what this thing actually is. You and I are watching two institutional giants, NASA and the UN, tell fundamentally different stories through their actions. One says, relax. The other activates planetary defense protocols. One says it's natural. The other treats it like target practice. And the deadline for answers is already counting down. December 9 is the mid-campaign check-in, when coordinated data from observatories worldwide gets compiled and analyzed. That's just days away from when this video releases. December 19 is closest approach to Earth. That's 2 weeks out. And January 27 is when the UN exercise officially concludes and we get the final assessment. These aren't vague future dates. These are concrete moments coming fast, and what gets revealed in those windows matters. Here's the thing that should make you pause. Planetary defense exercises aren't new. The International Asteroid Warning Network has run 7 of these before. They've practiced coordinating global response to potential impact threats. They've refined communication protocols between agencies. They've tested how quickly observatories can share data when time matters. This is a proven system that's been operational for over a decade. They know how to do this. But every single exercise before this one used a known asteroid already in our solar system, objects with predictable orbits, objects we've tracked for years, objects that behave exactly how physics says they should behave. Safe, controlled practice scenarios where the variables are understood and the outcomes are expected. 3I Atlas is none of those things. It came from beyond our solar system, from a star system we'll never visit, carrying composition and behavior we've never seen before. Its trajectory is hyperbolic, meaning it's not bound by our sun's gravity. It's passing through and leaving forever. It doesn't follow the rules our solar system objects follow because it wasn't born here. And right now, as it swings around the sun and makes its closest pass by Earth, it's displaying behavior that has scientists arguing with each other in published papers and public interviews. So the question isn't just why they chose 3I Atlas. The question is why now? Why this specific object during this specific window? And why extend the exercise more than a month past closest approach if the entire point is just tracking something as it flies by? Think about that for a second. If you're practicing planetary defense coordination, you'd want to focus on the critical window when the object is closest and moving fastest, when tracking is most difficult and reaction time matters most. That peaks on December 19, but the exercise runs until January 27, 5 weeks after closest approach, 5 weeks after the object has already passed Earth and is heading back out into interstellar space. What are they monitoring during those 5 additional weeks? This isn't speculation or conspiracy thinking. This is just reading the timeline they published and asking the obvious question that timeline creates. If there's no threat, if this is just a natural comet, if NASA's position is accurate, then why does the UN's Planetary Defense Network need 2 months to watch it, with most of that time spent monitoring what happens after it's already gone past us? You might be thinking this is routine bureaucracy, that large institutions always overprepare, that this is just standard scientific caution. And maybe that's true, but that explanation requires you to ignore the specifics. It requires you to not notice that this is the first interstellar object ever used for this purpose. It requires you to overlook the fact that 3I Atlas started showing unusual activity right when the exercise launched. It requires you to dismiss the scientists at Harvard and other institutions who are publicly stating this object has characteristics that don't match natural formation. The contradiction isn't subtle. It's not hidden in technical jargon or buried in footnotes of reports. It's right there in plain sight. NASA says no threat. The UN treats it as a target. Both are documented. Both are official. Both are happening simultaneously. And here's what makes this even more pressing. We're not waiting years for answers. December 9 is days away. That's when the first major data compilation gets released to the coordinating agencies. December 19 is 2 weeks out. That's maximum observation opportunity when 3I Atlas is closest to Earth and every major telescope will be watching. January 27 is less than 2 months away. That's when the exercise concludes and the final assessment gets published. This timeline isn't theoretical. It's active. It's unfolding whether we're paying attention or not. And the gap between what we're told and what we're seeing is wide enough to drive questions through. So here's what we're going to do together. We're going to examine what the UN exercise actually involves, what they're specifically tracking, and why the technical challenges of monitoring an interstellar object matter more than you'd think. We're going to break down the timeline and see what the dates reveal about intent. We're going to look at the scientific anomalies that make 3I Atlas different from every comet we've studied. We're going to hear from the scientists who are speaking out, both those who think this could be artificial and those who think that's ridiculous. And we're going to connect all of this to the bigger picture of what planetary defense preparation actually means in an era where interstellar visitors are becoming more common. If this contradiction bothers you the way it bothers me, if you're the kind of person who notices when official statements don't match official actions, hit that like button. Drop a comment and tell me whether you think the UN knows something NASA isn't saying publicly, or whether this really is just coincidental timing and scientific caution. Because one way or another, we're about to find out which interpretation is closer to the truth. The countdown has already started, and the first checkpoint is only days away. Let's break down what's really happening here, starting with what this UN exercise actually is, and why choosing 3I Atlas for it matters more than any official statement is letting on. Before we can understand why using 3I Atlas for this exercise is significant, you need to know what this system actually does and why it exists in the first place. The International Asteroid Warning Network isn't some theoretical working group that meets once a year to discuss hypotheticals. It's an operational coordination body established in 2014 under the United Nations Office for Outer Space Affairs. Its entire purpose is to organize the global response if we ever detect an object that poses a genuine impact threat to Earth. We're talking about the real infrastructure that would activate if something dangerous was actually coming. IAWN connects space agencies, observatories, research institutions, and governments across every continent. When it activates, hundreds of telescopes point at the same target. Data gets shared in real time. Trajectory calculations get refined continuously. Risk assessments get updated as new information comes in. Communication protocols kick in to alert decision makers. This is the system that would tell world leaders whether we have months, years, or decades to respond to an actual threat. And it's not untested. Since its establishment, IAWN has run coordinated exercises to stress test the network, identify bottlenecks in data sharing, improve calculation accuracy, and practice the human coordination side of planetary defense. Because when you're dealing with something that could impact Earth, you don't want to be figuring out who calls who or which data format everyone uses while the clock is ticking. You practice in advance. That's what these exercises are. Controlled rehearsals using real objects that pose no actual danger, but allow the network to practice like it's real. The first exercise used an asteroid already known and tracked. The second did the same. The third, fourth, fifth, sixth, and seventh exercises all followed the pattern. Pick a near-Earth asteroid with a well-understood orbit. Coordinate global observation, practice data sharing, refine communication between agencies. Improve the system's response time. 7 exercises. 7 solar system objects. 7 predictable, understood, safe practice scenarios. And then came Exercise 8. On the 27th of November 2025, IAWN launched its 8th coordinated campaign. The target was 3I Atlas, an object from beyond our solar system currently making its closest pass by Earth. For the first time in the program's history, they chose something that wasn't born in our solar system. For the first time, they selected a target with an interstellar trajectory that doesn't play by the gravitational rules our models are built on. For the first time, they picked an object displaying behavior that scientists are actively debating in real time. Now, the official explanation for this choice is straightforward. According to the statements released by IAWN, interstellar objects present unique technical challenges for observation and trajectory prediction. These objects have hyperbolic orbits, meaning they're not gravitationally bound to our sunday. They move faster than solar system objects. Their composition is unknown because they formed in different stellar environments. They can outgas unpredictably as they heat up near the sun, which changes their trajectory in ways that don't follow simple gravitational calculations. All of this makes them harder to track accurately. That explanation makes sense. On paper, using 3I Atlas as a practice scenario to prepare for future interstellar visitors is logical. It's forward-thinking. It acknowledges that Oumuamua in 2017 and Borisov in 2019 established a pattern. Interstellar objects do occasionally enter our solar system. We need to be ready to track them. Practicing with 3I Atlas while it's here is good preparation. But here's where logic and timing create friction. The exercise didn't start when 3I Atlas was first detected months ago. It didn't begin when scientists had already established its trajectory and confirmed it wasn't going to hit Earth. It launched on November 27, right as the object began showing unusual activity. Right as reports started circulating about brightness fluctuations that repeat on a 16-hour cycle. Right as spectroscopic observations detected nickel vapor at distances from the Sun where nickel shouldn't be vaporizing. Right as debate erupted about whether this thing was fragmenting or staying intact despite stresses that should tear it apart. The timing aligns too precisely with the anomalies becoming public knowledge. Let me be clear about what this exercise involves in practical terms. Hundreds of observatories are currently pointing instruments at 3I Atlas. They're conducting astrometry, which means precisely measuring its position in the sky over time to calculate its trajectory down to incredible accuracy. They're doing photometry, which tracks brightness changes that reveal rotation rates, surface composition, and outgassing events. They're performing spectroscopy, analyzing the light coming off the object to identify what chemicals are present and in what concentrations. Some facilities are using radio observations to look for anomalies in how the object interacts with the solar, wind, and space environment. All of this data is being coordinated through IAWN. Observatories share their findings in real time. Multiple independent measurements get cross-checked to eliminate errors. Trajectory predictions get refined as more data comes in. Risk assessments get updated continuously. This is the full apparatus of global planetary defense operating at full capacity, and it's not a short exercise. Most previous IAWN campaigns ran for a few weeks, focusing on the critical observation window when tracking mattered most. Exercise 8 runs from the 27th of November 2025 all the way to the 27th of January 2026. 2 full months. That's longer than any previous exercise. Why? If the goal is just practicing coordination and data sharing, you don't need 2 months. You could accomplish that in 2 weeks during the closest approach window. If the goal is just tracking an interstellar object to refine techniques, you'd focus on the period when it's brightest and easiest to observe, which peaks around closest approach on December 19. But this exercise extends 5 weeks past that peak. It continues monitoring 3I Atlas well after it's passed Earth and is heading back out toward interstellar space. The object will be dimmer, farther, harder to track. Observing it will require more telescope time and more resources for less return on basic trajectory data. So what are they tracking during that extended period? The official timeline includes a mid-campaign check-in on December 9. That's when all participating observatories submit their coordinated findings to IAWN for compilation and analysis. This check-in happens 10 days before closest approach. Why 10 days before? Why not wait until after closest approach when you'd have maximum data? Unless the point of the December 9 check-in is to assess something before closest approach arrives, to see whether the data collected so far changes any predictions about what will happen during and after the close pass. That phrasing matters. What will happen? Not just where the object will be, but what it will do. December 19 is closest approach. 3I Atlas swings past Earth at its nearest point. This is when every major observatory will have instruments locked on. This is when brightness will peak and observation conditions will be optimal. This is when whatever is going to happen during the close pass will happen. And then the exercise continues. Through late December, through early January, all the way to January 27, more than 5 weeks after the object has already flown past us. You don't monitor something for 5 additional weeks after it passes unless you're watching for aftermath, unless you're tracking whether something changes post-perihelion after the object has rounded the sun and is heading back out, unless you're looking for behavior that manifests later, not immediately. Comets often fragment after perihelion because the thermal stress of passing close to the sun weakens their structure. The heat gets inside through cracks, vaporizes subsurface ice, and the pressure blows them apart days or weeks later. We've seen this with solar system comets many times. If 3I Atlas fragments, it might not happen on December 19. It might happen in early January, as delayed thermal stresses propagate through whatever this thing is made of. But we've also seen comets that should have fragmented stay mysteriously intact, objects that by all models should have broken apart but didn't. And when that happens, when something survives conditions it shouldn't survive, scientists start asking different questions about what it's made of and whether their assumptions about its structure are wrong. IAWN is positioning this exercise to capture both scenarios. If 3I Atlas fragments, they'll track the debris field and practice coordinating observations of multiple pieces. If it stays intact, they'll have data showing an object survived, stresses it theoretically shouldn't survive, which tells them something fundamental about its composition and structure. Either outcome provides valuable information, but only one outcome would be truly surprising in a way that demands explanation. The structure of this exercise, the timeline, the choice of target, all of it suggests preparation for something more complex than just practicing coordination. It suggests they're using this real-time event to gather data on an object that's already displaying characteristics that don't fit the models. It suggests that calling this just an exercise might be technically accurate but functionally incomplete. Because if this were only about practicing coordination with a convenient interstellar target, you wouldn't need the extended timeline. You wouldn't need the December 9 early check-in. You wouldn't need 2 months of continuous monitoring when 3 weeks would cover the critical window. But if this is about using a legitimate practice exercise as cover for intensive scientific investigation of an object that's behaving strangely, then suddenly the timeline makes perfect sense. The UN gets to activate planetary defense infrastructure without declaring an emergency. NASA gets to maintain its official position that there's no threat. Scientists get access to coordinated global observations they'd never get for a purely academic research project. And the public gets told this is routine practice, while the actual work being done goes far deeper than practice requires. That's not conspiracy, that's just institutional pragmatism. You use the tools and frameworks available to accomplish the work that needs doing without triggering panic or having to explain complexities to a public that might not understand the nuances. But it does mean that when NASA says no threat and the UN activates planetary defense, both statements can be technically true while still concealing the more interesting truth underneath. No impact threat doesn't mean no mystery. No danger to Earth doesn't mean nothing unusual is happening. And calling something an exercise doesn't mean the data being collected is hypothetical. This brings us directly to the next question that won't let go once you see it. If the timeline alone raises questions, wait until you see what the timeline is actually documenting as it unfolds. Let's put the dates on the table and watch the pattern reveal itself. The 27th of November 2025. The UN's International Asteroid Warning Network officially launches Exercise 8, designating 3I Atlas as the target for coordinated global observation. Hundreds of observatories receive notification. Data sharing protocols activate. The 2-month monitoring campaign begins. Late November, just days after the exercise launches, reports surface about a newly discovered characteristic of 3I Atlas. Scientists observing the object detect what they're calling a heartbeat pattern. The object brightens and dims on a precise cycle, roughly every 16 hours, not random fluctuations, not chaotic outgassing, a repeating pulse with clockwork regularity. The discovery gets published in observational bulletins. the scientific community starts debating what could cause such precise periodicity. The 1st of December 2025, news outlets start picking up the story with headlines about 3I Atlas erupting. Reports describe jets of material shooting off the object, brightness surges, activity that makes the comet suddenly more visible and more interesting. The public narrative shifts from this being just another interstellar visitor to this being an active, dynamic object doing things in real time that we can watch. The 9th of December 2025. The mid-campaign check-in arrives. IAWN compiles coordinated data from participating observatories worldwide. This is the first major analysis checkpoint, happening 10 days before closest approach, 10 days before the object reaches its nearest point to Earth. Whatever the global network has observed so far gets evaluated here. Trajectory models get updated, behavior patterns get assessed. Decisions presumably get made about what to focus on during the critical December 19 window, the 19th of December 2025. Closest approach, 3I Atlas passes Earth at its minimum distance, still millions of miles away but as near as it will ever be. This is the observation peak, maximum brightness, optimal viewing conditions. Every major telescope that can point at it will point at it. Spectroscopy, photometry, radio observation, radar if possible. This is the data collection moment that justifies the entire exercise. Late December through early January. Expected window for JWST observations. The James Webb Space Telescope, our most powerful space observatory, has time allocated for post-perihelion observations of 3I Atlas. These observations weren't scheduled for before closest approach. They're scheduled for after, once the object has rounded the Sun and is heading back out. JWST will use its infrared instruments to analyze chemical composition, surface temperature, structure, and look for characteristics that can't be seen from ground-based telescopes. The 27th of January 2026, the UN exercise officially concludes. Final data compilation, final assessment, 2 full months after launch, and 5 weeks after closest approach, the coordinated campaign ends. Whatever conclusions can be drawn from 2 months of intensive global observation will be drawn here. Now step back and look at what that timeline actually describes. The exercise didn't launch when 3I Atlas was first detected. It didn't begin during initial trajectory calculations months ago, when scientists confirmed this was an interstellar object. It launched in late November, right as unusual activity started being documented, right as the heartbeat pattern became apparent, right as the object transitioned from interesting to anomalous. Then 4 days after the exercise launches, the eruption activity hits the news cycle. 4 days. That's barely enough time for the observatories to get coordinated and start producing data. It's not enough time for the exercise to have caused the discovery, but it's perfect timing for the exercise to have been launched because someone already knew the object was doing something unusual and wanted coordinated observation in place when that activity intensified. The December 9 check-in is positioned 10 days before closest approach, not after, when you'd have complete data, before. Why do you need to analyze preliminary findings before the main event unless those findings might change how you approach the main event? Unless what you're seeing in late November and early December is unexpected enough that you need to assess and adjust before the object gets even closer? Think about what that implies. If this were purely a practice exercise, you wouldn't need a mid-campaign adjustment point. You'd just collect data through closest approach and compile it afterward. But if this is intensive scientific investigation disguised as practice, then a December 9 checkpoint makes perfect sense. It's the moment where you look at what the object has done so far and decide whether your observation strategy for closest approach needs to change based on what you're learning. December 19 is obvious. That's the peak moment. But here's what's not obvious until you think about it. Most objects become less interesting after closest approach. They're moving away, getting dimmer, harder to observe. Data quality declines. There's less scientific return for the same amount of telescope time. Under normal circumstances, you'd concentrate resources on the approach and close pass, then scale back observation as the object recedes. This exercise does the opposite. It extends 5 full weeks past closest approach, maintaining intensive coordinated observation well into January. That's not routine. That's not efficient. That's expensive in terms of telescope time and coordination resources. You don't do that unless you have specific reasons to watch what happens after perihelion. and we know from historical examples what those reasons might be. Comets fragment post-perihelion. The thermal stress of passing close to the Sun doesn't always manifest immediately. Sometimes, it takes days or weeks for the heat to propagate through the object's interior, vaporize subsurface ice, build up pressure, and cause structural failure. When comets break apart, it often happens after they've already passed the Sun and are heading back out. If 3I Atlas fragments, January is when it would happen. The extended timeline captures that window, but there's another possibility the timeline accommodates. If 3I Atlas doesn't fragment, if it survives intact despite going through thermal and gravitational stresses that should break it apart, that's equally important data, maybe more important, because intact survival when fragmentation is expected means the object is either much stronger structurally than models predict, or it's made of something unusual, or it's not what we think it is at all. Scientists have already published papers questioning whether 3I Atlas is actually a comet. Some proposals suggest it's a fragment of an exomoon or planetary crust from another star system, geologically processed material rather than primordial ice and rock. If that's true, it would explain why it's behaving differently from known comets. It would explain the chemical composition anomalies. It would explain why it might survive perihelion intact when a normal comet wouldn't. The timeline is built to resolve that question. By running the exercise through January 27, IAWN ensures they'll have data showing whether the object fragmented or not. They'll know if the structural integrity assumptions were correct. They'll have before and after measurements that tell them what this thing actually is. Then there's the JWST observation window. Those observations aren't scheduled randomly. They're timed for post-perihelion, after 3I Atlas has been heated by the Sun and any surface chemistry changes have occurred. JWST's infrared instruments can detect temperature variations, chemical signatures, and structural features that ground-based telescopes can't see. If there's anything unusual about this object's composition or behavior, JWST will find it in late December or early January, which means the UN exercise timeline perfectly overlaps with the most critical scientific observation windows. It starts before closest approach to establish baseline measurements. It peaks during closest approach when observation conditions are optimal. It extends past closest approach to capture fragmentation or intact survival. And it runs long enough to incorporate JWST data before concluding. That's not coincidence. That's design. Someone planned this timeline to capture specific information during specific windows. The exercise framework provides the coordination infrastructure. The extended duration provides the data continuity. The checkpoints provide adjustment opportunities. And the January 27 conclusion provides enough time to assess everything that happens post-perihelion before making final determinations. If you were trying to intensively study an anomalous object without declaring an emergency or admitting publicly that you're concerned about what you're seeing, this is exactly how you'd structure it. Launch a legitimate planetary defense exercise using the object as a practice target. Use that framework to justify the coordination and resource allocation. Maintain the official position that it's routine preparation. And quietly gather every piece of data you can during the critical windows, when the object's true nature might reveal itself. The dates don't lie. November 27 launch as activity starts. December 9, early checkpoint before closest approach. December 19 observation peak. Late December JWST follow-up. January 27. Conclusion after post-perihelion window closes. Every milestone is positioned to capture information about what this object does, not just where it goes. And that raises the question nobody's answering publicly. If this timeline is just about practicing coordination, why position it so precisely around the moments when 3I Atlas is most likely to reveal what it actually is? Why invest 2 months of intensive global observation in an exercise when 3 weeks would accomplish the stated goals? Unless the stated goals aren't the real goals. Unless practice is the cover story and investigation is the actual mission. Unless NASA can keep saying no threat because that's technically true, while the UN uses its planetary defense network to figure out what they're actually looking at. The timeline makes sense if you understand what it's really tracking. Not just trajectory, not just position, but behavior, activity, composition, response to solar heating, structural integrity. Everything that would tell you whether this object is what we expect or something we've never encountered before. Which brings us to the next layer. If the timing raises questions, Wait until you hear what they're actually observing during this carefully constructed timeline. Because the more you learn about what 3i Atlas is doing, the stranger it gets. The official explanation for choosing 3i Atlas as the target for Exercise 8 comes down to one phrase repeated in multiple statements. Unique technical challenges. Interstellar objects present unique technical challenges that solar system objects don't. That's the reasoning. That's why this exercise is necessary. That's why they picked something from beyond our solar system instead of another near-Earth asteroid. And on the surface, that explanation holds. Interstellar objects genuinely are more difficult to track and predict than solar system natives. Let me walk you through why that's true, because understanding the real challenges makes the anomalies more striking when you see them. First, trajectory. Objects in our solar system follow elliptical orbits governed entirely by the sun's gravity. Their paths are predictable. We can calculate where they'll be decades or centuries from now with incredible precision because the physics is straightforward. Gravity pulls them into closed loops around the sunday. They come back. They repeat. The math is clean. Interstellar objects don't do that. They're on hyperbolic trajectories, meaning their paths are open curves. They swing in from the depths of space, pass through our solar system once, and leave forever. They're not bound by our sun's gravity. They're moving fast enough to escape. That makes their paths harder to predict because small variations in velocity matter more. A tiny acceleration from outgassing or some other force can shift the trajectory in ways that compound over time. You need more precision in your measurements and more sophisticated models to account for variables that wouldn't matter for a captured asteroid. Second, composition. Solar system objects formed from the same primordial material that created our sun and planets. We know what they're made of because we've studied thousands of them. We know what chemicals are common, what ratios to expect, how they behave when heated. Our models are built on that foundation. Interstellar objects formed around different stars in different molecular clouds with different chemical environments. Their composition is unknown until we measure it. They might contain elements or compounds in ratios we've never seen. They might behave differently when heated because their structure and chemistry reflect alien stellar conditions. Every interstellar visitor is a first contact scenario with the chemical fingerprint of another part of the galaxy. Third, outgassing. Comets accelerate as they heat up near the sun because frozen volatiles vaporize and jet material into space, creating thrust. For solar system comets, we know what volatiles to expect. Water ice mostly, with carbon dioxide, carbon monoxide, and various organics. The outgassing is predictable enough that we can model it and account for the trajectory changes it causes. Interstellar comets might outgas different chemicals in different ratios. They might respond to solar heating in ways our models don't expect. And if their outgassing behavior is unpredictable, then the trajectory changes it causes are unpredictable, which makes it hard to forecast where they'll be with the precision planetary defense requires. All of that is legitimate. Those challenges are real. Using 3i Atlas to practice tracking an object that doesn't follow solar system rules makes sense for preparing the network to handle future interstellar visitors. But here's where the explanation starts fraying at the edges. Because 3i Atlas isn't just challenging in the ways interstellar objects are supposed to be challenging. It's displaying characteristics that challenge our understanding of what these objects are. Let's start with the heartbeat. Observers first documented this in late November. The object brightens and dims on a regular cycle, approximately every 16 hours. Not random variations, not chaotic fluctuations you'd expect from tumbling or irregular outgassing. A repeating pattern with consistent periodicity. At first glance, that sounds like rotation. The object spins, and as different parts of the surface face our direction, we see brightness changes. One side reflects more light, the other less. As it rotates through a cycle, we see the bright side, then the dim side, then the bright side again. That's normal. Lots of objects do that. But the pattern isn't smooth. It pulses. It surges in brightness and then drops in a way that suggests active outgassing timed to the rotation. Every time the object completes a cycle, material jets off in bursts. Not continuously, not randomly. On a timer. What causes that? One possibility is that the rotation exposes frozen volatiles to sunlight in a specific region of the surface. When that region rotates into sunlight, it heats up, the ice vaporizes, and jets shoot out. Then the rotation carries that region back into shadow, the outgassing stops, and the brightness drops. 16 hours later, the cycle repeats. That explanation works if the outgassing site is localized to one area and the rotation is stable. But for the pattern to be this regular, the rotation has to be incredibly stable. No wobble, no precession, no chaotic tumbling. Just clean, steady rotation with one side consistently outgassing when exposed to light. That's unusual. Most comets don't rotate that cleanly, especially if they're outgassing, because the jets create torque that changes the spin over time. You'd expect the period to vary. You'd expect the brightness pattern to evolve as the rotation changes. But 3I Atlas maintains a 16-hour cycle with almost mechanical precision. Mechanical precision. That phrasing shows up in some of the scientific discussion, not as in artificial, but as in unnaturally regular for a natural object. It's precise enough that it looks like a machine keeping time rather than a chaotic chunk of ice and rock. Now, add the chemical composition anomalies. Spectroscopic observations detected nickel vapor in the coma surrounding 3I Atlas. Nickel is a metal. It doesn't vaporize easily. You need significant heat to turn solid nickel into gas. And 3I Atlas started showing nickel vapor at distances from the Sun, where temperatures shouldn't be high enough to vaporize nickel. It's too far out. The Sun's not hot enough at that distance. So, either the object contains nickel in a form that vaporizes more easily than solid metal, or something else is heating the surface beyond what sunlight alone should produce, or the composition is so unusual that our assumptions about temperature don't apply. Then there's the carbon dioxide to water ratio. Normal comets are mostly water ice, with smaller amounts of carbon dioxide and other volatiles. When they heat up near the Sun, water dominates the outgassing. That's the standard comet behavior we've observed for decades. 3I Atlas shows the opposite pattern. It's releasing carbon dioxide at levels much higher than water. The ratio is inverted compared to what we expect. 8 parts carbon dioxide to 1 part water, when it should be the other way around. Why would an interstellar comet have that composition? If it formed in a cold molecular cloud around another star, it should still have accumulated mostly water ice, because water is one of the most common molecules in space. Carbon dioxide should be present, but secondary. Unless this object formed in an environment we've never observed, or under conditions that favored carbon dioxide over water in ways our models don't account for. Or unless it's not a comet. Some scientists have proposed that 3I Atlas might be a fragment of geological material from an exomoon or exoplanet, crustal rock that was blasted off a larger body in a collision and sent drifting through interstellar space. If that's true, the composition makes more sense. Planetary crusts contain metals. They contain carbon dioxide locked-in minerals. They wouldn't have the water-rich composition of a primordial comet because they're not primordial. They're processed material from a differentiated body. But if it's crustal rock, why is it outgassing? Rocks don't jet material into space unless they're heated enough to vaporize surface compounds, or unless they contain trapped volatiles that release under solar heating. And if it's a geological fragment, why the regular 16-hour pulse? Rocks don't typically have mechanisms that create periodic outgassing unless their structure is unusually organized. This is where the explanations start multiplying without converging. Every answer raises another question. Every model that solves one problem creates another inconsistency. Then there's the fragmentation question, which might be the most revealing aspect of all. 3I Atlas passed perihelion, the point of closest approach to the Sun, on the 29th of October 2025. That's when thermal stress is maximum. That's when comets often break apart because the heat gets inside, vaporizes subsurface ice, and the pressure blows them into pieces. We've watched this happen to multiple comets over the decades. It's a well-understood process. Before perihelion, some scientists predicted 3I Atlas would fragment. The thermal models suggested it should. The stresses should exceed the structural strength of a typical comet. They expected it to break into multiple pieces that would gradually drift apart as they continued moving away from the Sunday. As of right now, there's debate about whether it fragmented or not. Some observations suggest possible fragmentation or shedding of material. Others suggest the nucleus stayed intact. The data isn't conclusive yet, which is part of why the exercise extends into January. They're watching to see whether delayed fragmentation occurs or whether the object definitively survived intact. If it fragmented as predicted, that supports the natural comet interpretation. It behaved the way comets behave, Mystery solved, mostly. But if it stayed intact, that's harder to explain. That means the structural integrity exceeded models. That means whatever this thing is made of is stronger or more cohesive than expected. That means either our assumptions about its composition are wrong, or it's not a natural comet, or it has internal structure that's preventing fragmentation. Avi Loeb, the Harvard astrophysicist who's been most vocal about the possibility of artificial origins for anomalous interstellar objects, has stated publicly that intact survival would be significant evidence. Natural comets fragment under these conditions. If 3I Atlas doesn't, it suggests intentional structure, something designed to stay together. Something manufactured rather than naturally formed. That's a massive leap, obviously. Intact survival alone doesn't prove artificial origin. There could be natural explanations we haven't thought of, but it would be another data point in the column of things that don't fit expectations. And when you stack enough anomalies, the explanations that work for each one individually start to strain when you try to make them all fit together. 16-hour mechanical precision in outgassing, nickel vapor at impossible distances, inverted CO2 to water ratio, possible intact survival through conditions that should destroy it. Each one might have a natural explanation, but all of them in the same object starts looking less like bad luck and more like a pattern. And patterns demand explanation. This is what makes 3I Atlas uniquely challenging in ways that go beyond the official statements. Yes, interstellar objects are harder to track. Yes, their composition is unknown. Yes, their behavior is less predictable. But those challenges are expected. Scientists anticipated those. What they didn't anticipate is an object that checks every box for unexpected behavior simultaneously. That pulses like clockwork. That releases the wrong chemicals at the wrong temperatures in the wrong ratios. That might be surviving conditions it shouldn't survive. That's not just challenging, that's anomalous. And anomalies are what get planetary defense networks activated, whether anyone wants to use that word publicly or not. Which leads directly to the question of what the hundreds of observatories coordinating through IAWN are actually looking for. Because if you know what they're measuring and why those measurements matter, the picture of what's happening becomes a lot clearer. When the International Asteroid Warning Network activates, hundreds of observatories don't just point their telescopes in the same general direction and hope for the best. This is coordinated scientific data collection operating at a level most people never see. Let me take you inside what's actually happening right now, in real time, as 3I Atlas moves through our solar system. Astrometry is the foundation. This is precise positional measurement. Observatories photograph the object against the background stars and measure exactly where it is in the sky, down to fractions of an arcsecond. They do this repeatedly over hours and days and weeks. Each measurement adds to the dataset that allows calculation of the trajectory with incredible precision. For an object moving on a hyperbolic orbit like 3I Atlas, astrometry is critical because small variations in position over time reveal changes in velocity that indicate forces other than gravity are acting on it. Outgassing creates thrust. As volatiles jet off one side of the object, Newton's third law applies. Every action has an equal and opposite reaction. The object accelerates slightly in the opposite direction of the jets. Those accelerations are tiny, but they compound. Over weeks and months, they add up to trajectory shifts that matter. If you're trying to predict where the object will be in January based on observations from November, you need to account for every bit of non-gravitational acceleration. Otherwise, your predictions drift away from reality. So astrometry isn't just tracking where 3I Atlas is. It's tracking how its trajectory is changing in ways that reveal what forces are acting on it beyond gravity. And if those forces don't match what outgassing models predict, that's a flag. That's something that needs explanation. Photometry is the next layer. This measures brightness over time. Not just how bright the object is, but how that brightness changes minute by minute, hour by hour, day by day. These measurements are what revealed the 16-hour heartbeat pattern. They're what show when outgassing events happen. They're what detect whether the object is getting brighter or dimmer as it moves through different regions of space. Brightness changes tell you about surface activity. A sudden brightening means something just released a burst of material that's reflecting sunlight. A gradual brightening as the object approaches the sun is expected. But if brightness surges on a regular timer, that's rotation-modulated outgassing. If brightness spikes unpredictably, that's chaotic activity that might indicate fragmentation or structural instability. Right now, Photometry stations are watching 3i Atlas for any changes in the pattern. Is the 16-hour cycle staying consistent, or is it changing? Are the brightness surges getting stronger or weaker? Is there any indication the object is breaking apart, which would show up as multiple brightness peaks that gradually separate in time as fragments drift away from each other? The December 9 check-in will compile all the photometry data collected since late November. Scientists will analyze whether the heartbeat pattern is stable or evolving. They'll look for any signs of fragmentation or structural change. They'll compare the brightness behavior to models and see whether it matches predictions or deviates in ways that demand revised assumptions. Spectroscopy is where things get chemically interesting. This technique analyzes the light coming off 3i Atlas to identify what elements and molecules are present. Different chemicals absorb and emit light at specific wavelengths. By spreading the light into a spectrum and measuring which wavelengths are present or missing, you can identify the composition of the gas and dust surrounding the object. This is how scientists detected the nickel vapor. Nickel has a distinct spectral signature. When you see those specific wavelengths in the spectrum, you know nickel atoms are present in the coma. Same with carbon dioxide, water, carbon monoxide, sodium, iron, and everything else they've identified. But spectroscopy also reveals temperature. The intensity and distribution of spectral lines tell you how hot the material is. The Doppler shift of the lines tells you how fast the gas is moving. The ratios of different chemicals tell you what's vaporizing and in what proportions. Right now, spectroscopy is answering questions like, is the CO2 to water ratio staying constant or changing as the object heats up? Are new chemicals appearing that weren't detected earlier? Is the temperature of the outgassing gas consistent with solar heating alone, or is there evidence of additional heating from internal processes? If the spectroscopy shows chemicals that shouldn't be present, or temperatures that don't match models, or ratios that contradict comet formation theories, that's data that forces re-evaluation. And that's data the UN exercise is collecting in coordinated form so multiple observatories can cross-check each other's findings and eliminate instrumental errors. Radio observation adds another dimension. Radio telescopes don't look at visible light. They detect radio waves emitted by charged particles and plasma. When an object like 3i Atlas interacts with the solar wind, the stream of charged particles flowing out from the sun, it creates a region of disturbed plasma around itself. Radio telescopes can detect that disturbance. They're also sensitive to certain molecular transitions that emit radio waves. Carbon monoxide, for example, can be detected in radio wavelengths even when it's hard to see in visible light. Radio observation can reveal the extent and distribution of the gas cloud surrounding the object in ways optical telescopes can't. But here's what makes radio observation particularly interesting. If there were any organized electromagnetic activity associated with 3i Atlas, radio telescopes would be most likely to detect it. Natural objects don't emit organized radio signals, but artificial transmitters do. SETI, the search for extraterrestrial intelligence, uses radio telescopes to listen for signals that would indicate technological origin. Nobody's officially calling this SETI observation, but multiple radio facilities are pointed at 3i Atlas as part of the coordinated exercise. They're nominally looking at plasma interaction and molecular emission, but the data they collect would also reveal any anomalous radio signals if they existed. Is anyone checking for that specifically? Publicly, no. But the data exists. If there were organized radio emissions coming from the direction of 3i Atlas, they'd be in the dataset whether anyone was looking for them or not. And once data exists, it eventually gets analyzed. Now, layer in the coordination aspect. All of these observatories, doing all of these different types of observation, are sharing their data in real time through the IAWN network. That means astronomers can cross-reference findings immediately. If one facility detects a brightness surge, others can check their data from the same time window and see if they saw it too. If spectroscopy shows a chemical spike, photometry can check if there was a brightness change at the same moment. This cross-referencing eliminates false positives. It confirms real events. It builds a complete picture of what the object is doing from multiple independent perspectives simultaneously. That's the power of coordinated observation. You're not relying on one dataset from one facility. You're synthesizing hundreds of datasets into a comprehensive understanding. And that's what makes the December 9 check-in significant. It's the first moment when all that coordinated data gets compiled and analyzed together. Individual observatories have been submitting their findings, But December 9 is when IAWN synthesizes it all and produces an integrated assessment. What will that assessment show? If everything is behaving as expected, the data will confirm 3I Atlas is a normal interstellar comet with predictable outgassing and composition. The trajectory will match gravitational models, plus expected outgassing thrust. The spectroscopy will show typical comet chemicals in typical ratios. The photometry will reveal rotation and outgassing that fits standard comet behavior. But if the data shows persistent anomalies, if the trajectory has unexplained accelerations, if the chemistry doesn't match any comet we've studied, if the photometry reveals patterns that don't fit natural rotation and outgassing, then the December 9 assessment will tell scientists they're looking at something that needs a different explanation. And that assessment happens privately first. IAWN coordinates space agencies and research institutions. They share findings within the network before releasing anything publicly. The December 9 check-in isn't a press conference. It's an internal data compilation for the participating agencies. Which means if there's anything in the data that raises serious questions, the agencies will know about it days before the public does. They'll have time to analyze it, time to discuss it, time to decide how to communicate it, or whether to communicate it. December 19 is closest approach. That's the big observation moment. Maximum data collection. But the December 9 assessment determines how they approach December 19. If the preliminary data from late November and early December shows everything is normal, then December 19 observation plans stay standard. But if the preliminary data shows anomalies, December 9 is when they'd adjust the observation strategy to focus on those specific mysteries during the closest approach window. That's why the timing of the check-in matters. It's not just administrative bookkeeping, it's a decision point. An opportunity to redirect resources toward the most important questions based on what's been learned so far. And then there's the extended timeline through January. What are they watching for during those additional weeks after closest approach? Post-perihelion fragmentation is the obvious answer. But there's more. After an object passes the sun and heads back out, its outgassing behavior changes. The side that was heated on approach cools down. The side that was in shadow starts facing the Sunday. If there's compositional variation across the surface, you'd see different outgassing patterns after perihelion compared to before. Any changes in behavior during that post-perihelion window tell you about internal structure and composition. If the outgassing suddenly stops, that suggests surface volatiles were depleted and there's nothing underneath to replenish them. If outgassing continues or even intensifies, that suggests deeper reserves or internal heating that's not just surface-level solar warming. If the heartbeat pattern changes frequency or amplitude post-perihelion, that reveals something about the rotation or the internal structure that's controlling the pattern. If it stays exactly the same, that's equally informative because it means whatever mechanism is driving the periodicity is stable and consistent through thermal and gravitational stress. This is forensic-level investigation. That word forensic has appeared in some of the scientific papers and technical reports describing the observation campaign. Forensic monitoring. As if they're analyzing a crime scene, or at least something that needs extremely detailed documentation to understand what happened. You don't use forensic-level investigation for routine scientific observation. You use it when something doesn't add up, and you need every piece of evidence you can collect to reconstruct events. When the obvious explanation doesn't fit, and you need to rule out alternatives systematically. So what are they really tracking? On the surface, they're tracking trajectory, composition, rotation, outgassing, and structural stability of an interstellar comet during a planetary defense exercise. That's the official description, and it's accurate. But functionally, they're tracking whether 3I Atlas behaves the way a natural object should behave. They're collecting data comprehensive enough to either confirm it fits within our understanding of how these objects work, or to document that it doesn't and force a re-evaluation of what we're actually looking at. The network is designed to detect threats. But threats aren't just about impact trajectories. A threat is anything we don't understand that's operating in near-Earth space. And right now, we don't fully understand what 3I Atlas is doing, or why. The coordination, the timeline, the forensic-level detail, all of it suggests this exercise is documenting something that's already raised questions privately. Questions serious enough to justify 2 months of global observation. Questions that need answering before the object leaves our solar system forever and we lose the opportunity to study it. Which brings us to the people actually doing the analysis and what they're saying publicly about what they're finding, because the scientific community is not speaking with one voice on this. And that division itself tells you something important. The scientific debate around 3I Atlas isn't happening in the shadows. It's playing out in academic papers, public interviews, and social media exchanges between researchers who fundamentally disagree about what we're observing. And that disagreement exists at the highest levels of astrophysics, between scientists with impeccable credentials and decades of experience. This isn't fringe theorists versus the establishment. This is establishment versus establishment. Avi Loeb is the most visible voice suggesting 3I Atlas might not be what we assume it is. For those unfamiliar, Loeb is a Harvard professor, former chair of Harvard's astronomy department, founding director of Harvard's Black Hole Initiative, and chair of the advisory board for the Breakthrough Starshot Initiative. He's published hundreds of papers in peer-reviewed journals. His academic credentials are unimpeachable. Loeb has stated publicly that he estimates a 30 to 40% probability that 3I Atlas has artificial origins. Not certainty, not wild speculation. A probability assessment based on the observable characteristics that don't fit natural comet models. He's pointed specifically to the heartbeat pattern, the mechanical precision of the periodicity, and the chemical composition anomalies as evidence that deserves consideration beyond the default assumption of natural formation. In interviews released in late November and early December, Loeb used the phrase active intelligence in reference to the possibility that the outgassing pattern could be controlled rather than passive response to solar heating. He's not claiming it's an alien spacecraft. He's saying the data doesn't conclusively rule out technological origin, and that the scientific community should be willing to investigate that possibility rather than dismissing it reflexively. Loeb also commented on the intact survival question. He stated that if 3I Atlas passes perihelion without fragmenting, that would be significant evidence supporting non-natural origins. His reasoning is straightforward. Natural comets are loose aggregations of ice and rock, held together by weak gravitational self-attraction and frozen volatiles. When heated intensely and subjected to gravitational tidal stress, they come apart. If 3I Atlas stays together, it suggests structural integrity beyond what natural comet formation produces. To be clear, Loeb isn't saying it's definitely artificial. He's saying the probability is high enough that serious scientific investigation is warranted, and that dismissing the possibility without thorough analysis is bad science. He's arguing for open-minded inquiry based on evidence, rather than assumption based on expectations. On the opposite side is Brian Cox, the British physicist and science communicator. Cox has been dismissive of any suggestion that 3I Atlas might be artificial. In public statements and social media posts, he's called such ideas drivel and urged people to stick to reliable sources and not get distracted by sensational claims. Cox's position represents the mainstream scientific consensus. Interstellar objects are expected to exist. We've now seen 3 in recent years. Their behavior might be unusual compared to solar system comets, but that's because they formed in different environments and have different compositions. Jumping to artificial origin explanations when natural explanations are still viable is unnecessary and irresponsible. It feeds public misunderstanding and distracts from the real science. This is a legitimate scientific disagreement about methodology and interpretation. Cox represents the conservative approach. Stick with natural explanations until they're definitively ruled out. Loeb represents the exploratory approach. Investigate all possibilities that fit the data, including ones that challenge assumptions. Neither position is inherently wrong. Science needs both. Conservatism prevents wild speculation from being taken seriously before evidence supports it. Exploration prevents missing genuine discoveries because they don't fit existing frameworks. But what's striking about this debate is the intensity. Cox isn't gently disagreeing with Loeb. He's publicly dismissing his suggestions as irresponsible. Loeb isn't quietly proposing alternatives in technical papers. He's actively pushing the conversation into public forums and media interviews. That intensity suggests the stakes feel high to both sides. Cox sees a threat to scientific credibility if alien explanations get traction without sufficient evidence. Loeb sees a threat to scientific progress if legitimate anomalies get ignored because they make people uncomfortable. And they're not the only voices in this conversation. A recent academic preprint from late November proposes 3I Atlas as a crustal fragment from an exomoon or exoplanet based on reanalysis of observational data. They suggest the object might be a crustal fragment from an exomoon or exoplanet, not a primordial comet, but geologically processed material that was ejected from a larger body in a collision and has been drifting through interstellar space, potentially for millions of years. This explanation accounts for some of the chemical oddities. Planetary crusts contain metals. They contain carbon dioxide locked in carbonate minerals. They've been heated and compressed and altered by geological processes that change their composition from primordial material. If you blast a chunk of crust off an exomoon and send it tumbling through space, it would have composition unlike typical comets. The paper doesn't suggest artificial origin. It's proposing a natural but unusual formation scenario that explains why 3I Atlas doesn't behave like normal comets. It's a fossil from a dead world, essentially. A piece of alien geology that happens to be passing through. That explanation is more conservative than Loeb's position, but still represents a departure from calling this just another comet. It acknowledges the anomalies demand explanation beyond standard comet formation models. Then there's the institutional positioning. NASA's official statements remain cautious and conservative. They describe 3I Atlas as a natural interstellar comet. They acknowledge it's being studied intensively. They confirm there's no impact threat to Earth, but they haven't commented publicly on the specific anomalies or the scientific debate about artificial origin possibilities. The European Space Agency has been similarly measured. They're participating in the observation campaign. They're contributing data, but their public communications stick to confirmed facts and avoid speculation. The United Nations, through IAWN, has said even less. They announced the exercise. They described it as practice for tracking difficult objects. They haven't addressed why they chose this specific object or commented on any of the scientific debate. That silence from institutions while individual scientists argue publicly is telling. Institutions are conservative by design. They don't make claims they might have to retract. They don't fuel speculation that could create public panic or undermine credibility. They wait until evidence is conclusive before making definitive statements. But individual scientists aren't bound by institutional caution. They can propose ideas, debate interpretations, and push boundaries in ways institutions can't. That's how science progresses. Individuals explore possibilities, debate them, test them, and eventually the evidence converges toward conclusions that institutions can then adopt. What we're seeing right now is that exploratory phase playing out in public. Loeb is proposing artificial origin as a possibility worth investigating. Cox is pushing back and defending natural explanations. Other researchers are proposing intermediate scenarios like crustal fragments. The debate is active, messy, and unresolved, and that's appropriate for something genuinely anomalous. If 3I Atlas were clearly just a comet, there'd be consensus. If it were clearly artificial, there'd be emergency response. But it's in the ambiguous middle zone where the data doesn't definitively support any single explanation and multiple interpretations remain viable. That ambiguity is what makes the UN exercise so important. The Coordinated Global Observation Campaign is collecting data at a level of detail that might resolve the ambiguity. By January 27, when the exercise concludes, we'll have trajectory data comprehensive enough to know whether non-gravitational accelerations fit outgassing models or suggest something else. We'll have spectroscopy detailed enough to confirm or rule out composition scenarios. We'll have photometry showing whether the heartbeat pattern stayed stable or evolved. We'll know whether the object fragmented or survived intact. That data will either narrow the possibilities or expand the mystery. Either it will confirm 3I Atlas fits within our understanding of natural interstellar objects, just with unusual characteristics, or it will document that the anomalies persist and demand explanations that challenge current models. The scientists arguing right now will have that data to work with. The debate will continue, but it will be informed by better evidence. And eventually, the scientific community will converge toward consensus as more is understood. But until then, the fact that serious scientists are having serious disagreements about what this object is tells you the question isn't settled. NASA can maintain its position. The UN can coordinate planetary defense. Brian Cox can dismiss speculation. Avi Loeb can suggest artificial possibilities. All of those positions coexist because the evidence hasn't yet forced resolution. And that brings us to the most immediate question facing everyone watching this unfold. What actually happens in the next several weeks? What are the specific moments when we'll learn more? What should we be watching for? And what will those reveals tell us about whether the conservative interpretation or the exploratory interpretation is closer to the truth? We're not waiting years for answers. We're not even waiting months. The timeline ahead of us is compressed into specific days and weeks, each one bringing new information that moves this story forward whether we're paying attention or not. The 9th of December 2025 is the mid-campaign check-in. This is when the International Asteroid Warning Network compiles the first major assessment of coordinated data collected since the exercise launched on November 27. Every participating observatory has been submitting their findings: astrometry showing trajectory updates, photometry documenting brightness patterns, spectroscopy revealing chemical composition, radio observations tracking plasma interaction. All of that data gets synthesized into an integrated report. This report isn't published publicly, at least not initially. It goes to the participating space agencies, research institutions, and government entities that coordinate through IAWN. They see the compiled findings first. They analyze what the data shows. They discuss what it means. And they decide how to adjust observation priorities for the critical December 19 closest approach window based on what's been learned. That's the function of a mid-campaign check-in. It's not ceremonial. It's operational. If the data from late November and early December reveals unexpected behavior, December 9 is when they identify it and redirect resources to focus on those anomalies during the peak observation moment 10 days later. So what might the December 9 assessment show? If the heartbeat pattern is stable and continues with mechanical precision, that's confirmation the 16-hour periodicity is real and consistent, not a temporary fluctuation. If the pattern is changing, that tells them the rotation or outgassing mechanism is evolving as the object heats up. If spectroscopy confirms the inverted CO2 to water ratio persists, that strengthens the case that this isn't a normal comet and demands explanation through alternative formation scenarios. If new chemicals appear in the spectrum, that reveals compositional complexity that wasn't apparent in earlier observations. If astrometry shows trajectory deviations that don't match outgassing models, that flags non-gravitational forces that need accounting. If trajectory predictions are tightening and matching models, that suggests the object is behaving predictably despite the chemical oddities. Whatever the assessment shows, it sets the stage for December 19. December 19 is closest approach. This is the moment 3I Atlas passes Earth at its minimum distance. It's still millions of miles away, no danger of impact, but as close as it will ever be. For telescopes on Earth, this is peak visibility, maximum brightness, optimal observation conditions. Every major facility that can point at it will point at it. This is when spectroscopy will be most detailed because the object is brightest and more photons are available for analysis. This is when imaging will be highest resolution because the object is nearest. This is when any surface features, fragmentation, or structural details will be most visible. If there's anything to see, December 19 is when we see it. But closest approach to Earth isn't perihelion. 3I Atlas already passed its closest point to the Sun in the 29th of October 2025. So, by the 19th, it's already been heated to maximum temperature and is starting to cool down as it moves away from the Sunday. This timing means December 19 observations will show post-perihelion behavior. How the object responds after maximum heating, whether it's fragmenting, whether outgassing is decreasing or continuing, whether the structure held together or is coming apart. If fragmentation happened, December 19 will confirm it. Telescopes will see multiple pieces instead of a single nucleus. Photometry will show multiple brightness peaks that don't align in time. Astrometry will track multiple trajectories diverging from each other as fragments separate. If the object stayed intact, December 19 will document that too, a single consolidated nucleus. One brightness pattern corresponding to one object. No evidence of structural failure despite the thermal stress of perihelion. That distinction matters immensely. Fragmentation means natural comet behavior. Intact survival means something stronger, more cohesive, potentially more organized than a natural comet. Then the timeline extends into late December and January, and this is where things get particularly interesting. The James Webb Space Telescope has observation time allocated for 3I Atlas in the post-perihelion window. JWST is the most powerful space observatory we've ever built. Its infrared instruments can see things ground-based telescopes can't. It can detect surface temperature variations. It can analyze chemical signatures with precision unavailable from Earth. It can image structure and features at resolutions that reveal details invisible to anything else. JWST observations weren't scheduled for before closest approach. They're scheduled for after. Why? Because post-perihelion is when the object has been thermally processed by the Sun, and any changes to surface chemistry or structure will be apparent. It's when you'd detect residual heat that doesn't match solar heating alone. It's when you'd see how the object is settling after maximum stress. If there's anything unusual about 3I Atlas that requires infrared analysis to detect, JWST will find it in late December or early January, and that data will feed into the final analysis before the UN exercise concludes. The 27th of January 2026 is the official end date for Exercise 8. By this point, the object will be dim, distant, and heading out of the inner solar system toward interstellar space. Observation will become increasingly difficult as it recedes. The coordinated campaign will conclude because there's diminishing scientific return on continued monitoring. But before it ends, IAWN will compile the final assessment, 2 months of data, observations from hundreds of facilities, trajectory refined to precision, composition analyzed in detail, behavior documented through approach, perihelion, closest approach to Earth, and departure. Everything synthesized into conclusions about what this object is, what it did, and what that means for future interstellar visitors. That final report is what we're waiting for. That's the document that will either confirm 3I Atlas was a natural interstellar comet with unusual but explainable characteristics, or it will document persistent anomalies that demand further investigation and challenge our assumptions about what these objects can be. Will that report be released publicly? Partially, probably. Space agencies typically publish summaries of scientific findings, but the full technical report, the internal analysis that goes to government and institutional stakeholders, that might remain restricted or heavily redacted depending on what it contains. This is where transparency and caution collide. If the report concludes everything was natural and predictable, there's no reason to restrict it. Full disclosure, publish the science, add to our understanding. But if the report documents genuinely anomalous findings that can't be explained by current models, institutions face a harder decision. Release everything and risk public misunderstanding or panic? Release summaries and maintain institutional caution? The precedent suggests they'd choose controlled disclosure. Enough information to inform the scientific community, but carefully worded to avoid fueling speculation. Regardless of how they choose to communicate it, the January 27 conclusion marks the end of our opportunity to study this object in detail. After that, 3I Atlas continues outbound. It dims. It recedes. Eventually it becomes too faint for even the most powerful telescopes to track. It disappears back into interstellar space, and we never see it again. Which means these next several weeks are the window. This is our chance. This is when we learn what we're going to learn, and the timeline is structured to capture everything that matters during that window. December 9 tells us what the preliminary data shows and how they're adjusting the observation strategy. December 19 gives us maximum detail at closest approach and confirms fragmentation or intact survival. Late December and early January add JWST's infrared perspective. January 27 synthesizes everything into final conclusions. If you're following this story, those are the dates that matter. Those are the moments when information emerges. You won't get real-time updates unless you're inside the network, but scientific findings typically get published or leaked within days or weeks of internal analysis. So expect news to surface around each of those checkpoints. And expect the debate to intensify. As data becomes available, scientists will analyze it, interpret it, and argue about what it means. Loeb will look for evidence supporting artificial origin possibilities. Cox will emphasize natural explanations. Other researchers will propose intermediate scenarios. The conversation will be active, messy, and public. That's actually healthy. That's how science works when something genuinely uncertain is being investigated. Multiple interpretations compete until evidence forces convergence. The debate isn't a sign that scientists don't know what they're doing. It's a sign they're honestly grappling with data that doesn't fit neatly into existing frameworks. But it also means you're going to see contradictory headlines. You're going to read claims and counterclaims. You're going to encounter certainty from people who are interpreting the same data in fundamentally different ways. And you're going to have to decide who to trust and what to believe based on your own assessment of the evidence and the credibility of the sources. What I can tell you is that the UN exercise is real. The data being collected is real, the timeline is fixed, and the checkpoints are coming whether anyone's ready for them or not. December 9 is days away, December 19 is 2 weeks out, January 27 is less than 2 months away. This isn't distant future speculation. This is immediate near-term reality. And that reality is about to tell us something important about 3I Atlas, about interstellar objects, and about whether our assumptions about what's possible in the universe need updating. The countdown is running, and the answers are coming fast. Step back from the technical details and the scientific debate for a moment and ask the bigger question. Why does any of this matter? Why should you care whether 3I Atlas is a natural comet or something stranger? Why does it matter that the UN activated planetary defense protocols while NASA maintains there's no threat? Because this is about more than one object passing through our solar system. This is about how we respond to the unknown in an era where the unknown is becoming more common. 3I Atlas is the third confirmed interstellar visitor we've detected in 8 years. Oumuamua arrived in 2017, tumbling through our solar system with a trajectory and acceleration profile that sparked years of debate about whether it was a natural asteroid or something artificial. Borisov came in 2019, more clearly a comet, but still unusual in composition and behavior. Now 3I Atlas in 2025, displaying characteristics that have scientists divided once again. 3 visitors in 8 years. That might not sound like much, but consider the context. We've been watching the sky for centuries, and in all that time, we never confirmed an interstellar object until 2017. Now we're seeing them regularly. That's not because they suddenly started arriving. It's because our detection capabilities improved enough to spot them, which means there are more we haven't seen. There are smaller objects, darker objects, objects on trajectories that didn't bring them close enough to Earth to be noticed. Interstellar space is full of debris ejected from other star systems. Rogues from planetary formation, fragments from collisions, material blasted off worlds by impacts, all of it drifting through the galaxy, occasionally passing through stellar systems like ours. We're just now beginning to see that population, and every time we detect one, we're learning that our assumptions about what these objects are and how they behave need revision. Oumuamua taught us that interstellar objects can have unusual shapes and acceleration profiles that don't fit simple models. Borisov taught us that interstellar comets exist but have different compositions than solar system comets. 3I Atlas is teaching us that behavior can be periodic, precise, and difficult to explain with natural outgassing models. Each visitor has expanded our understanding and challenged our assumptions. Each one has been stranger than the models predicted. And that pattern suggests we're still in the early phase of figuring out what the interstellar population actually looks like. Which brings us to planetary defense and why practicing with these objects matters. Planetary defense isn't just about detecting asteroids that might hit Earth decades from now. It's about being ready for anything unusual that enters our space. It's about having systems in place to rapidly assess threats, coordinate global response, and take action if needed. And increasingly, it's about dealing with objects we don't fully understand. If an interstellar object entered our solar system on a trajectory that posed genuine impact risk, we'd have very little time to respond. These objects move fast. They don't orbit the sun on predictable cycles. They pass through once, and if they're going to hit Earth, the warning time might be measured in months or even weeks depending on when we detect them. That's why exercises like the one running right now matter. IAWN is refining its ability to quickly characterize interstellar objects, predict their trajectories with precision despite non-gravitational forces, and coordinate global observation even when the object is unfamiliar and behaving unexpectedly. They're practicing the human coordination side too. Who communicates what information to whom? How do you share data across institutional and national boundaries in real time? How do you maintain accuracy when hundreds of observatories are submitting findings that need cross-checking? How do you make decisions quickly when time matters? These are operational questions that have to be worked out in advance. You don't want to figure out communication protocols while an actual threat is approaching. You practice now so the system works smoothly when it matters. But there's another layer to this that doesn't get discussed as openly. Planetary defense preparation is also about maintaining calm. It's about demonstrating that institutions have plans, that systems are operational, that humanity has the capability to detect and respond to threats. Public confidence in preparedness reduces panic when something unusual happens. If 3I Atlas were approaching and no exercise had been announced, imagine the speculation that would dominate social media and news coverage. Is it dangerous? Is the government hiding something? Why aren't they doing anything? But because there's a visible, coordinated response happening publicly, those questions are defused. Yes, we're watching it. Yes, we're coordinating globally. Yes, we have systems in place. Calm maintained. That's strategic communication. Transparency about preparedness reduces fear. Even if the real work being done goes deeper than what's discussed publicly, the visible exercise provides reassurance. Now think about what happens if the January 27 final report documents that 3I Atlas had characteristics we can't explain with natural formation models. What happens if the data shows persistent anomalies that challenge our understanding of what these objects are? One possibility is that scientists propose new natural formation scenarios we hadn't considered. Maybe there are environments around other stars that produce objects with composition and behavior we don't see in our solar system. Maybe geological processes on exomoons create crustal fragments with unusual properties. Maybe there are comet formation mechanisms in interstellar space that differ from what happens in protoplanetary disks. New natural explanations that expand our models without requiring artificial origin hypotheses. That's the conservative scientific path, and it's probably where the consensus will eventually land because natural explanations are always more likely than artificial ones, statistically speaking. Space is big, natural processes are common, and artificial objects are rare. But there's another possibility that can't be dismissed without evidence. Maybe we encounter something that genuinely doesn't fit any natural explanation we can construct. Maybe the periodicity, the composition, the structural integrity, all of it stacks up in ways that strain natural models past the breaking point. Maybe the data forces consideration of intentional design. If that happens, it doesn't mean immediate confirmation of alien technology. It means the question gets escalated to more intensive investigation. It means resources get allocated to study the next interstellar visitor even more carefully. It means SETI gets more funding because if artificial objects are passing through, we need to know. It means the conversation shifts from, these are natural objects we need to understand, to some of these might not be natural and we need to determine which. That shift would be profound. Not because it proves aliens exist, but because it changes how we approach the search. It moves from theoretical SETI radio listening to practical object investigation. It turns the search for extraterrestrial intelligence into something happening in our solar system, not just distant star systems. And regardless of whether 3I Atlas turns out to be natural or not, the fact that we're having this conversation at all shows we're in a new era. An era where interstellar visitors are common enough that we're detecting them regularly. An era where our observation capabilities are good enough to document their characteristics in detail. An era where anomalies get noticed and debated publicly rather than dismissed quietly. That's progress. That's humanity maturing into a spacefaring species that pays attention to its cosmic environment and takes seriously the possibility that we're not alone or that the universe is stranger than our models predict. So yes, it matters whether 3I Atlas is natural or artificial. It matters what the data shows. It matters that institutions are coordinating response and refining capabilities. It matters that scientists are debating openly. All of that matters because it's part of learning how to exist in a universe where unknowns are routine and preparation is essential. And it matters on a personal level too. You're watching this unfold in real time. You're seeing the scientific process work. You're witnessing humanity practice for scenarios that might seem like science fiction but are increasingly routine reality. You're part of a moment where our understanding could shift based on what gets revealed in the next several weeks. That's rare. That's worth paying attention to. And that's why the questions we started with still don't have answers, but those answers are coming fast. Let's bring it back to where we started and see what we still don't know. NASA says there's no threat. The UN made 3I Atlas an official target for Planetary Defense Exercise 8. Both statements are documented, both are current, both appear contradictory. Why? The surface explanation is that no threat means no impact risk, and targeting just means using it for practice. That's technically correct. But it doesn't explain why this specific object was chosen for this specific exercise after 7 previous exercises used solar system objects. It doesn't explain the 2-month timeline that extends far past closest approach. It doesn't explain the December 9 early check-in positioned before the critical observation window. If you accept the surface explanation, the contradiction dissolves. NASA is addressing impact risk. The UN is practicing coordination. No conflict. But if you look at the timeline, the choice of target, and the behavior that target is displaying, the surface explanation feels incomplete. It answers the narrow question while ignoring the broader context. So the real question might be, what aren't we being told, and why? Maybe nothing is being hidden. Maybe institutional caution and measured public communication is creating the appearance of concealment, when actually scientists are just being careful not to overstate conclusions before evidence is definitive. That's reasonable. That's responsible. That's how institutions should behave. Or maybe there's information that raises questions serious enough to justify intensive investigation but not serious enough to warrant public alarm. Maybe the UN exercise is using a legitimate framework to gather data on something anomalous without triggering panic by calling it anomalous publicly. That's also reasonable. That's pragmatic institutional behavior that balances transparency with responsibility. We don't know which interpretation is correct because we don't have access to the internal communications and preliminary data that space agencies are reviewing privately. All we have is what's visible publicly: statements, timelines, scientific debate, and the exercise itself. Which leads to the next unanswered question. Why choose the first interstellar object for exercise 8 when 7 previous exercises worked fine with solar system asteroids? The official explanation is that interstellar objects present unique technical challenges worth practicing. That's true, but Oumuamua was available in 2017 and 2018 when exercises 5, 6, and 7 happened. IAWN could have used it then. They didn't. Borisov was available in 2019 and 2020. They didn't use it either. Why wait until 3I Atlas in 2025 to finally practice with an interstellar target? One answer is that 3I Atlas has a better trajectory for observation. Maybe Oumuamua and Borisov didn't provide optimal practice scenarios because of their geometry or timing. Maybe 3I Atlas was the first interstellar object with characteristics that made it genuinely useful for exercise purposes. Another answer is that 3I Atlas is displaying behavior that makes it particularly interesting, and the exercise framework provides a way to study it intensively, using resources and coordination that wouldn't be available for a purely academic research project. That's not hiding anything. That's opportunistic use of available infrastructure. Either way, the choice was deliberate. Exercises are planned months in advance. The decision to use 3I Atlas was made knowing it would be controversial and would raise questions. They did it anyway. That suggests the benefits outweighed the communication challenges of explaining why. Why extend the exercise more than a month past closest approach? If the goal is practicing coordination, you'd focus on the critical window when the object is nearest and tracking is most difficult. That peaks on December 19. Extending through January 27 adds 5 additional weeks of observation when the object is dimmer, farther, and less interesting from a pure trajectory tracking perspective. The fragmentation monitoring explanation makes sense. Comets fragment post-perihelion, and tracking debris fields is valuable practice. But you'd know within a week or two whether fragmentation occurred. You wouldn't need 5 weeks unless you're watching for delayed fragmentation that happens much later than typical, or unless you're monitoring post-perihelion behavior for other reasons. Changes in outgassing patterns, evolution of the heartbeat periodicity, spectroscopic shifts as the object cools, structural characteristics revealed by how it responds to thermal stress over time. All of that is scientifically valuable, but it's not really planetary defense practice. It's scientific investigation, which again suggests the exercise framework is being used for purposes that go deeper than the stated goals. What does the December 9 check-in actually show? We won't know immediately. The assessment is internal to IAWN and participating agencies. But information leaks, scientists talk, papers get published. Within days or weeks after December 9, we'll start seeing analyses and interpretations appearing in academic forums and media coverage. If the preliminary data confirms standard comet behavior, that'll be communicated to reduce speculation. If the data shows persistent anomalies, that might be communicated more carefully, or it might leak through scientists who disagree about how to interpret it. Either way, December 9 is the first major checkpoint where we'll get a sense of whether the exercise is producing expected results or unexpected questions. Will 3I Atlas fragment or stay intact? This is the most concrete question with the clearest implications. Fragmentation supports natural comet interpretation. Intact survival challenges it. By late December, we'll know. Observations will show either multiple pieces or a single nucleus. If it fragments, the debate shifts to why it behaved anomalously before fragmenting. If it stays intact, the debate intensifies around what that implies about composition and structure. Loeb has already stated that intact survival would significantly increase his probability estimate for artificial origin. Other scientists will push back and propose natural explanations for unusual structural strength. But the data will constrain which explanations are viable. What explains the 16-hour heartbeat pattern? Rotation-modulated outgassing is the standard explanation, but it requires incredibly stable rotation and localized outgassing sites that maintain periodicity through thermal stress and gravitational perturbations. That's possible, but unusual. Alternative explanations require internal mechanisms that regulate outgassing timing, geological structures that channel volatiles to specific vents, subsurface reservoirs that release pressure periodically, internal heat sources that cycle on and off. All of those are speculative. The data might narrow the possibilities, or it might leave the question unresolved if we can't distinguish between competing models with available observations. Why nickel vapor at distances where nickel shouldn't vaporize? This is a chemistry question that spectroscopy can address but might not resolve. If the nickel is in a form that vaporizes easier than metallic nickel, that could explain it. If there's additional heating from internal processes, that could explain it. If the composition is so unusual that our temperature models don't apply, that could explain it. Or it could remain unexplained if the data doesn't provide enough detail to distinguish between possibilities. Why the inverted CO2 to water ratio? This goes to formation, environment, and composition. If 3I Atlas is a crustal fragment rather than a primordial comet, the ratio makes sense. If it formed in an unusually carbon-rich environment around another star, that could explain it. If there's preferential depletion of water from surface layers, that could explain it. Again, multiple explanations exist. The data might favor one over others, or the question might remain open until we get more interstellar comet examples to compare against. What happens January 27 when the exercise concludes? We get the final report synthesizing 2 months of data into conclusions. That report will either confirm 3I Atlas was a natural interstellar comet with unusual but explainable characteristics, or it will document persistent anomalies that challenge current understanding and recommend further investigation. How that report gets communicated publicly depends on what it contains. If it's routine, full disclosure. If it's anomalous, expect careful wording that informs without alarming. And what happens after January 27? 3I Atlas continues outbound. It dims. It becomes too faint to track. It leaves our solar system forever. The opportunity to study it ends. But the questions it raised persist, and the systems we use to study it remain operational, ready for the next interstellar visitor. Because there will be another. Interstellar objects aren't rare anomalies anymore. They're part of the environment we operate in. And every time one arrives, we get better at detecting it, tracking it, and understanding what it is. That's the real story here, not whether 3I Atlas is natural or artificial, not whether NASA and the UN are contradicting each other, but that we're maturing into a civilization that pays attention to its cosmic environment and responds systematically when something unusual appears. The contradiction that opened this video might never be fully resolved to everyone's satisfaction. Maybe there's no hidden truth, just different institutional perspectives on the same reality. Maybe there's more to the story that we'll learn later. Maybe the ambiguity is the point, the thing that keeps us watching and questioning and demanding better answers. What I know is this. December 9 is days away. December 19 is 2 weeks out. January 27 is less than 2 months. Those dates are fixed. The information they'll reveal is coming. And whatever we learn, it'll either confirm our understanding or force us to update it. Both outcomes matter. Confirmation is valuable. Revision is progress. So stay curious. Watch the sky. Follow the data. Question the contradictions. And don't let anyone tell you that asking why NASA and the UN are telling different stories through their actions is somehow unreasonable. Contradictions demand explanation, and the countdown to those explanations is already running. If you've made it this far, you're the kind of person who doesn't accept surface answers when deeper questions exist. Drop a comment and tell me what you think is really happening here. Natural comet with unusual characteristics? Something stranger? Institutional caution concealing genuine uncertainty? I want to know where you land on this. And if you want updates as December 9, December 19, and January 27 bring new information, subscribe so you don't miss what happens next, because this story isn't over. It's just beginning. And the most interesting part might be what we learn when the exercise concludes and scientists finally have complete data to analyze. The universe is stranger than we assume, and sometimes, just sometimes, paying attention to the contradictions is how we figure out just how strange it really is.